Apparently you did. I just graded them on Canvas. If you have it in there, I don't know what the disconnect is. Hopefully we can figure it out. All right, today, like math-wise, is the most important day of the year. It's not bad. We'll do it together. So this is a math class. It's the most fun part, I think, personally, but I'm weird. I introduced it yesterday, but we're just gonna go like we're starting over again. I usually do this twice. So stoichiometry. I love it. Also known as picket fences. If you've heard your friends describe the picket fence, that's really stoichiometry. And it isn't exactly, but it kind of is, whatever. So just a couple of words here. You don't have to write these all down, but I'm going to use the word stoichiometry. It's a fancy word for saying we're going to apply math to balanced equations. It's how we compare amounts of things to each other. All right. A species, that word will be used occasionally. That just means any of the chemicals or ions involved in a chemical reaction. It's just the stuff that's there. So we're talking about salt being formed, like NaCl, we'd have Na, we'd have Cl2, we'd have NaCl. Those would be the three main species in that reaction. So you don't, and it's not tested, it's just a term I will use when I speak. All right, picket fences, they are not technically stoichiometry, but it's the words I use to describe the process of stoichiometry. Picket fences are a tool to systematically align your numbers and units to convert from a given number and unit to an unknown unit and number. All right, now in math, when you multiply things that have like ratios or fractions or whatever, you'll have like 19 over 25 times 2 over 16 times 3/5 or something like that. Okay. In chemistry, we would just say we have 19, 25, 2, 16, 3, and 5. That's all we're doing is eliminating the amount of times we write parentheses. It's the same exact, they call it unit analysis in math, and it's no different. We're just making a little fence out of it. In chemistry, this square here is pretty much always empty, and then we just work from there. All right, so that's the picket fence. Isn't anything to be scared of. In the picket fence, you multiply all the numbers on top. So whatever that would be, you multiply all the numbers on bottom, you get a number, and then you would divide the top by the bottom. If you have a calculator, multiply all the top, then put in parentheses that expression on the bottom. Okay. All right, so don't be intimidated by the picket fence. It's just a tool to line them up in a really simple way. Okay, then last, wait, is there another one? Oh, that was it. All right, so picket fences take advantage of the fact that anything that is on top and the bottom of a fraction can be eliminated from the number. So that didn't make sense. But what we mean here is if I have the unit of grams and I divide it by grams, I no longer have to worry about the unit of grams. They cancel each other out. If I had a mole and a mole, they would cancel each other out, and I would be left with just that unit. And that's what I want. The unit at the end will always equal the same as the unit at the end. I'm going to say that a lot. It's going to be really annoying, but I'm going to repeat it. So this process becomes pretty simple for you. Okay, so stoichiometry, species, picket fence. Let's have at it. Now, before we get any farther, you asked me, and I had learned this and I'd forgotten about it, so I looked it up this morning. You had asked me, how did Avogadro determine Avogadro's number? Here's the truth. He did not. He really had nothing to do with the determination of the number. So it's kind of complicated. It took me like 5 wiki pages to put this all back together, because I learned this, I did, in 1996, but that was a while ago. And I filed it in the I'm not ever going to worry about this again drawer. You know you have that in your filing cabinet. But here we go. So it's a big, long set of situations. Avogadro was a lawyer and got interested in science. That's dangerous right there. So Avogadro deduced that in order, I forgot. Avogadro was studying a reaction between H2 plus O2 forming H2O. And the things that were produced were pretty much consistent every single time. And it's complicated, but he said this could only work if the amount of atoms present here, it was a 2-to-1 ratio. Sorry, that's the part he said was consistent. He said the only way this ratio was always the same is if you have the same amount of atoms, even though it's a different substance. So he said if you have a certain amount of gas, you're going to have the same amount of atoms, a certain volume. Okay, so he was the first one to say that the number of atoms in an element must be the same. And that's where he ends up getting the name. He's the first one to say it, but he has no idea what they are. Okay, so he deduced that in order for this ratio to always be the same, the equal volumes of any two gases at the same temperature and pressure must hold equal number of particles. That's called Avogadro's law. Okay, so the volumes have to have the same amount of numbers. All right, Faraday is a whole completely different dude studying way different stuff. But in 1833, he discovered that in electrolysis, the amount of charge, also known as F, which are Faraday's, necessary to deposit 1 mole of monovalent ions in an electrode, cations at the cathode, anions at the anode, were always the same, irrespectively of the kinds of ions. Okay. Now, he came up with this constant. It's called Faraday's constant, 96485. We'll learn that way later in the year. But basically what he was saying is if I have lithium, which is a +1, if I have potassium, which is a +1, rubidium, +1, or a mono ion or monovalent, it has 1. All right, or a Cl minus or an F minus, some of your grades, a Br minus. He discovered in this electroplating, which electroplating is what makes this piece of metal shiny. It doesn't start that way. It comes out, it looks like a normal piece of metal. Then they put it in a liquid, they turn on electricity, and the metal, the shiny part, the chromium probably, it sticks to it. And Faraday noticed that, hey, as long as I have the same charge, whether it's positive or minus, it takes the same amount of energy or electricity to get this process to work. And he thought, hey, this is something, it's always the same. We're going to call it Faraday's constant. And we're going to say that it's the same for any amount of electron as long as you have the same amount of electrons. And it's the first time where we say a certain number of something is always constant. You're like, okay, I'm lost. Well, this is how science worked in the 1800s. They took 3 different people and came up with one idea. Okay, Millikan, he comes along and he discovers, and we studied Millikan, he found the charge of 1 single electron. Remember how he did that? Really complicated. But he discovered it to be 1.602, whatever, times 10 to the negative 19 coulombs per electron. So now we have a couple numbers. Is this fascinating, Joe? I figured. Okay, so we now had the charge of 1 electron, and we now had what the total amount for a specific amount was, total amount of charge. If we take that, Faraday's constant, and we divide it by Coulomb's constant, or his value of 1 electron, we get a number, and it's 6.022 times 10 to the 23rd. And what's that value? That's Avogadro's number, and they call it a mole.
So a guy named Avocado Friday and Telegram all came together and did a bunch of science stuff and decided that a really big number existed. That's called a mole.
There you go.
All right.
Would you rather I summed it up that way?
Yeah.
None. Look, do you see this right here? This is all your fault, not mine. Someone's fault. Okay, so here we go. So, my friends, even though Avogadro didn't really do anything to find the number, he got the name because he was the first to say there was a number. They were all the same. He didn't know what it was, but when they discovered it, they're like, we're ready to roll. We call it Avogadro's number. The prefix mol is short for molecules, because Avogadro really was saying that the gas molecules have to be the same. It says particles here, but molecules was shortened to moles, and life's great. Sound good? Anyone else feel like that was awesome and want to write a paper on it? Okay. No, I don't want to grade a paper. I'd collect it and throw it in the garbage. Okay. One more thing before we start. I got this tweet a long time ago. This is from Taylor Jordan. I taught him over 10 years ago. And he said, first semester of my PhD, and I'm still using the picket fence method for dimensional analysis. Thanks, Mr. Tom Davidson, for the lessons that have proven to be invaluable. So it says, if you have a 20 megawatt power plant, how many homes can it power, assuming a capacity factor of 0.6 and an average home uses 12,000 kilowatts per year? This process I'm teaching you isn't just for chemistry. It works for anything where you have to convert something to something and you're given conversion factors. So 0.6 and 12,000 kilowatts per year. He just put it all right here. He had days. He had years to days, days to hours, and he had his other, whatever these conversions. I don't know how to do this problem, but he had them all right there lined up. Okay, I had a girl once. She came years after I taught her, and she brought me a huge cinnamon roll. And she said, this is the thank you for teaching me how to do dimensional analysis. I was like, that's cool. And she's one of the head bakers at Neaters in Salt Lake. And she says the first thing she does when she hires someone new is teaches them how to change the recipes to up or downsize them. It's dimensional analysis. It's extremely useful everywhere. All right, so here we go. We talked about molar mass yesterday. We okay with that? All right, so don't write this down. Just listen. So stoichiometric calculations. From the mass of substance A, you can use the ratio of coefficients of A and B to calculate the mass of substance B if it's a product or, oh, I was moving. Nice shot. That was hard. Whatever, you can read. I was trying to double. Clearly my left and right's crossed over there. But we can find whatever we need as long as we have the masses and the ratio of coefficients. That was the other, I'm like, I'm missing a word here. So ratio of coefficients is something we should know what it is from now on, okay? Ratio, that's not the best combo, but whatever. The ratio of coefficients are the numbers that are in front of a balanced equation. So if I had 2Na plus Cl2, that's a plus sign. That gets worse. Whatever. Goes to 2NaCl. My ratio, that's like a number on top of another, would be 2Na per 1Cl2. Okay with that? 2 to 1. Or I could say 1Cl2 to every 2 NAs. That's the ratio of the coefficients. Or I could say 2Na to 2 NaCl. Or I could say 1Cl2 to every 2 NaCl. And there's whatever. It's just the numbers in front, and I can flip them over to do whatever I feel like. Okay, we're ready to actually do stuff. Here we go. Ratio of coefficients will be really important. Okay, these 1, 2, 3, 4s, you don't have to write them down, like for real, but it's what I'm going to try and follow every time we do it, because if you do the same thing every time, these eventually become super, not that bad. Okay, so here we go. You will be given a problem with a reaction. You're going to have to write it out and balance if it's not already written out and balanced for you. And it says how many grams of salt can be formed if you have 36 grams of sodium. If it ever says a sentence like that, you assume you have as much of the other thing as you need. You just, all right, well, I have a limited amount of sodium, but how much salt can I make? Okay, so step number one is always to balance the reaction. So take 30 seconds and balance it if you haven't already. If you're at the bottom of a page, I would start on the new page. This one's not very long, but they can get extremely long. That kid Taylor, just in the last year or two, was in a group that sent something up into space to study it. It was like micro, what was it? Crap. No, it was like microfilament something, whatever. And they were studying the transport rate of things in zero gravity. It was really interesting. He told it to me, like, that is cool. I don't know what you're talking about. Yeah, it was really interesting. I think he was at the U. He's a smart dude. Okay, here we go. I feel like you should have had this balance because I just did it for you, right? So since there's 2 here, I would have put a 2 here. Since that made 2 NAs, I would have put a 2 there, and I would have had a 1 here. Okay, that has that little light blue background for a reason. You'll notice that blue background's right here. Here we go. So balance the reaction, number 1, check, we did that. Find molar masses of the needed species. So in this problem, it asks for salt, which on the AP test, it won't say salt. That's pretty vague. It would say sodium chloride. But we need the 2 species of salt and sodium. So once again, we're assuming we have as much chlorine as we need, and it has nothing to do with the problem. So I'm going to go find on the periodic table the mass of sodium. And I'll see it's the big number in the Na box. It's 23 grams per 1 mole. You okay with that? And NaCl is 23 plus 35.5, and I'm rounding. And that's where I got the 58.5 grams per mole. Will you tell your partner if you know how to find molar masses when there's more than one type of atom? Tell them real quick. Okay with that? Okay. I said you okay with that? All right. Hopefully, at least one of you said yes, and the other one hopefully said yes. If they said no, help them out. All right, so here we go. When we find the molar masses, we're going to use them. Please notice these are ratios. I have 23 per 1 mole, 58.5 per 1 mole. Okay, number 2. Oh, second number 2. 2B, or not to be. Here we go. Set up picket fence with given number and unit at top left. Okay, so draw one of these. It's a flat line and 3 vertical lines. And I'll teach you how to know how many vertical lines eventually. Okay. Now, it says right here with given number and unit. So in this problem, did it give me a number?
36.
It gave me 36. And what was the unit? Grams of Na. Be thorough. If you're not thorough, you're going to really struggle on these. If you just put 36, like, you're already hosed. All right. In chemistry, there's a few things, few truths that we believe to be self-evident. One of them is this. Look at the screen. Everyone look at the screen. Whatever unit I start with will always be the unit that I move down and over. So just go ahead and put a grams of Na right there. So on 2B, we said set it up by starting with the thing I gave you, right? In B, move the given unit down and to the right until you have the unit you want. Okay, so what do I mean by that? I want to solve for grams of the NaCl. Are we okay with that? Thank you. Okay, so looking right here, I have grams of Na. Is that grams of NaCl? No. So I move down and over until I get the unit I want. So here we go. Grams of Na is on the bottom. I know that because this always goes here. So I look up here. Do I have a ratio with grams of Na in it? Right here, right? There are 23 grams per every what? 1 mole. So I'm going to put 23 per every 1 mole. And I'm going to make sure I still have Na. So for every 23 grams of Na, I have 1 mole of Na. We okay so far? All right. Now, tell your partner, this unit right here is going to go where? Tell them. All right, down over here. So right here, I have a mole of Na. And I look, and this comes from, that's why it has the colored background. It comes from right here. What's in front of Na? A 2. So I put a 2 right there. Now stick with me. I know that some of you already know what goes here, but let's pretend you don't. This is number 4. If you ever get stuck, then go to the end and work your way until you meet in the middle. What I mean by stuck is if you don't know what goes up here, well, let's figure it out. So follow my logic right here. The unit I want at the end is grams of NaCl, correct? So that means the unit at this end must be grams of NaCl. Has to be. The unit at the end will always be, finish my sentence, the unit at the end. Don't say grams right now, yes, but it could be different. But I'll tell you what, these 2 units, that's terrible, whatever. If they aren't exactly the same, then you did it wrong. Okay, so the unit at the end is always the unit at the end. Okay, I'm taking forever. Look right here. I have grams of NaCl. Do I have a ratio of grams of NaCl up here? I do right here. It is 58.5 grams per every what? 1 mole of NaCl. Okay, now this part, if you look right here, keep looking, keep looking, keep looking. This unit always matches that unit, right? This unit always matches that unit. Always. Look right here. This unit always matches that unit. So what must go here? Mole of NaCl. And what's in front of that from my balanced equation? A 2. Okay, now look at the screen for a second. This whole process is based on canceling out units. Grams of Na are on the top and on the bottom. Mole of Na are on the top and on the bottom. Mole of NaCl are on the top and the bottom. The only unit I have not canceled out is grams NaCl, which is what I want in my answer, which means I have it set up correctly. So here we go. Math-wise, does everyone know, is it okay if 2 over 2 is just 1? Okay, this step is really important. Math-wise, on this problem, it didn't matter because they just ended up to be 1 over 1, but they won't always be that way. So math, I take 36, I multiply it by 58.5, and I divide that answer by 23. All right, will you type that in? All right, who has an answer? Payne, what'd you get? 91? Anyone back 91 up? Good. In AP, we have a rule, and that is that in the calculator of 2 or 3 nerds shall every number be established. Right, 91. Thumbs up if you got 91 and you typed it in. It breaks my heart when you do everything right and you type things in your calculator wrong. So be careful. Okay, that we're going to repeat this process 1,000 times this year. That's an overestimation, but it will be more than 100 times. Okay, here we go. Ratio of coefficients. The ratio of your balanced equation that compares the moles of what you want. What you want goes on top. I wanted NaCl. What I don't want is Na. They go on the bottom. All right, this is a step that requires us to have a balanced reaction. So remember the apples and oranges? We don't compare them to each other, but we would use this step to change them to money. And then once you knew their value compared, then you could find out how much an orange was if you knew the value of an apple. I know it's kind of weird, but it's the language where we can compare things. Okay, ready? How many grams of iron are required to produce 80 grams of iron 3 oxide? So step number 1 is to balance the reaction. I will do it, but you need to get to this point. So I'm going to produce iron 3 oxide. So my 2 elements must be iron and oxygen. I put a 2 with oxygen because I know it's diatomic, right? Then it's iron 3 oxide. That means that iron's a +3, oxygen's a -2. So I have FeO, but I drop the 2, and then I have the 3, Fe2O3. Thank you, my friend. What's that? All right, keep going. When you're done, let me know. We'll dry. Oh. All right. What? I am. My own personal car, yes. My driver's ed car, no. Knock on wood. All right, here we go. So hopefully you've balanced it. Who's balanced it? Okay. I see a 3 and a 2, so I'm going to do the swapperoo. I'm going to do this in a different color. So in front of the 3, I have a 2. In front of the 2, I have a 3, and then I fix the iron. 4, 3, 2. How did you do on that one? What's that? All right, sweet. Okay, what are the 2 species we need to find the molar mass? All right, iron, which is here, and iron 3 oxide. So let's go ahead. I'll do iron. It's 54, isn't it? Oh, 56. I'm sorry. $160? No. Yeah. Is it 160 for iron 3 oxide? Man, I hate being smart. All right, so that is 160 grams per 1 mole. Fair enough? Okay, will you see if you can set up the picket fence on your own right now? Try it on your own first. If you're not there yet, like, it's fine. We're still friends. Okay, raise your hands if you have it set up. Okay, we'll wait a little longer then. Oh, sorry, Keely. All right, let's go ahead and attack it. We have people anywhere from like, I'm done, that made perfect sense, to I have no idea what to do. You're everywhere in between. Now be patient. Most people that are already done and like, this isn't hard, they had a chemistry last year. So they're in a different boat. After chapter 4 though, you're all in the same sinking boat. All right, they don't have any advantage anymore. Okay, here we go. I did that. Set up the picket fence with the given number and unit. So in the problem, it gave me 80 grams of iron 3 oxide, right? So I'm going to start with 80 grams Fe2O3. All right, 80 grams Fe2O3. Now, when I said that, if you're willing to be bold for a second, when I said that, I saw a lot of people erase. Anyone willing to admit they did not have 80 grams right there? All right, what did you have? Okay, I'll address that. What did you have? Someone raised their hand back there. Okay. Anyone else willing to tell me they did? What did you have? 56. Okay. So all of you did something very predictable. When it says start with the given number and unit, that's the one from the sentence, not the ones we found from the periodic table. Okay. The sentence said, how much is required to produce 80 grams? The start will always be given to you as part of the sentence in the problem. Does that help? The other two masses we find on the periodic table and we use them. Okay, so here we go. Based on this on this being my given unit, I'm going to take it down and over because I always do. All right, so I put grams of Fe2O3. Now I look up and I should have been more thorough. This was 160 grams of Fe2O3 for every 1 mole of Fe2O3. If I write it that way, then you'll see, oh, there is a ratio. I have a ratio where I have grams of Fe2O3. In fact, for every 160 of them, I have 1 mole. Fair enough. Who had that step correct? Who had this as your second piece of the picket fence? Raise your hands. All right, Davis, if you're okay with it, what did you have here? Okay, and that's extremely common. Did you have Fe here or Fe2O3? Okay, these have to match. And the 160 came from Fe2O3. All right, so you had 56.
I think I did backwards.
Did it backwards. Okay, well, we're going to practice. So be patient with yourselves. All right, so these units right here, at least the chemical, they'll always be the same. They might be grams or moles, but they'll still be Fe2O3. Okay, looking right here. This unit, mole Fe2O3, must come down here. So I'm going to write mole Fe2O3. Sorry, I switched colors. That might annoy someone. Okay. Then I have my ratio of coefficients. I'm going to go to the end and work my way back. I want to know grams of iron. That's what I'm trying to solve for here. Grams of Fe. So what must be right here? Grams of Fe. Because the unit, the end, will always be the same as the unit at the end. I'll say that again with highlighter. The unit at the end will always be the same as the unit at the end. Okay, now looking up here, we have 56 grams of Fe for 1 mole of Fe. So I'm ready to go. 56 grams of Fe per 1 mole of Fe. So tell your partner what must come up here. What unit? Mole of Fe. Okay, now there are numbers that come here. Tell your partner where you find the ratio of coefficients. All right, I find them in front of the formulas. So just Fe is a 4, right? In front of Fe2O3 is a 2. Now I'm ready to do math. If I were you, I would reduce 4 over 2 to just 2 over 1. That saves you some calculator effort. Okay, multiply all the top, multiply all the bottom, and then divide the two answers. This one's funny. My bad. I mean, not bad, but that's ironic. What number did I get? 56. That was just random luck. That doesn't happen where the number at the end is the number at the end. It's fine. Just math-wise, 80 over 160 is 1/2, which I multiply by 2 over 1, which is 1, which I multiply by 56. Don't worry, don't, if you're like so lost right now, who cares? If you got 56, we're golden. Who had 56? Raise your hands. Okay, that's progress. That's a lot of progress. All right. Well, let's do another one. Whoops, there's the answer. Whew, hope he didn't look. Double check me that it's 62, but I'm pretty sure. Did anyone do it already? Okay. Okay. Those are the things. That says 24 grams of mg per 1 mole of mg. Okay, give it your best shot, my awesome friends. Nobody saw that, but that trick worked perfect. And it rarely does.
Somebody told me she showed you the video.
Whoops, I guess I need that there.
Yeah. MG.
Say that louder.
Um,
You just round based on the 5.
the middle, yeah. One.
91.5 is great. You don't have to round on these. Wait a minute, did I do that right? Yeah, I'm sorry. Are they all ones? Why did I do 2, 1, 2?
Oh, it's the same.
Yeah. Because we were gonna have 2 over 2 anyway.
So it works. It's just not simplified.
Oh, no,
All right, so I have it up here. I'll walk it through in case you still need it. Well, what was the answer? 167? All right, I'm just gonna say 168. If you're offended by that, I apologize. Here we go. So I started my picket fence with the number and the unit that the problem gave me, which was 65 grams of mg. This unit here must come down and become this unit here. Grams is really always tied to a mole, 1 mole in fact, So I knew the top was mole of Mg. If I know this unit, then I knew that unit was mole of Mg. So far, okay? All right, then a lot of you by now know this, but I go backwards anyway. Grams of Mg, the unit at the end will always be the same as the unit at the end. I had that ratio right here. 62 grams of magnesium fluoride for every 1 mole of magnesium fluoride. And then these units will always match each other. And so then I knew I was ready to go. I looked up to the balanced chemical reaction to find these. And it was really nice because they were ones. All right. Even when I screwed up and I had a 2 over a 2, we still would have had it right because they would have reduced. So then I took 65 times 62 and divided it by 24. And there we go. Who had 168? Okay, the back rows. Maybe the front row is just too lazy. All right. We have, try this problem tonight. Let me rewrite it. So it was Na plus phosphate goes to Na3P. I want to know how many grams of phosphate, or sorry, phosphide, I shouldn't have said phosphate, that was my bad, are needed to make 100 grams of sodium phosphide. You can write that out or take a picture of it. Try and have that answer tomorrow, and we'll just see how it goes. Yep, you're welcome. All right, raise your hands real quick if you feel at least comfortable with one of those. Medium comfortable, raise your hands. Okay, not bad. I'll take like 90%. Whoops, upside down. All right, you guys are awesome. There's plenty more coming tomorrow, so don't think like we're done and you have to know how to do it.